These are the 11.1 video notes, and we're going to be looking at chi-square tests for goodness of fit. All right, so the chi-square statistic. First of all, it is chi-square. It is not the chi-square statistic. If you say chi-square to a statistician, they are going to cringe on the inside. So this is chi-square. I understand how hard that might be to say it properly. We're not really too concerned with saying it properly, but just be aware that this is chi-square statistic. The chi-square statistic is a measure of how far the observed counts are from the expected counts. The formula for the statistic is observed minus expected over expected, where the sum is over all possible values of the categorical variable. So we're looking at categorical variables here. This isn't something that's going to end up being quantitative. This is something that is purely categorical. And that definitely does determine what we can run these statistics on. It's kind of a weird mix between quantitative and categorical, where we're going to break down categories and look at proportions within those categories and then determine what is the likelihood of that happening. So what we've been looking at in the past few chapters is just one specific proportion. So like when we're looking at, like if we wanted to determine whether or not the M&M's Corporation was lying to us when they said that here's the distribution of these M&M's, we would pick one color and we would say, all right, you're telling us the blue M&M's are this proportion. Here's the proportion of M&M's I got in this bag of candy based on the proportion that I got in this bag of candy. What is the likelihood of that occurring given the proportions that you told me? Are your proportions correct or not? So we were only looking at one proportion to try to make a determination of if the entire thing made sense. The purpose of the chi-square is to look at all proportions. So we're not just going to look at the blue candy, we're going to look at all of the candies, and we're going to compare all of the candies' proportions and what they are told to us and see if the expected values of those proportions match up with what we're looking at. And if so, if there's some reasonableness to whether or not they do or do not work out, well, then we can say whether or not we think that the company is lying about the proportions of the candies and the bag, things like that. So the idea here is that we're not just looking at one proportion to try to determine whether or not something makes sense or not. We're going to look at everything. And there's a lot of things that go into this. Like, first of all, why, and we'll get into that a little bit more. So an important note, when calculating the chi-square, we are looking at the expected values, not at the expected proportions. So you're going to need to find the expected values based on the proportions. So not the expected proportions, this is the expected values. So if you're given a proportion and then you know the sample size, you're going to have to go through and you're just going to have to say that the sample size multiplied by the proportion, whichever proportion you're looking at, is equal to your expected value. And then every expected value, the sum of the expected values needs to be equal to the sample size. And then it's important to talk about the expected values as compared to the chi-square statistic. Every single one of these observations is going to end up over the expected statistic. We do observed minus expected squared over expected. Basically, this is like an error measurement. We're looking at like what is the error of this proportion. And we've got to put it over expected because we could end up with the same difference from observed to expected statistic, but if one thing is taking up 5% and another thing we expect to take up 90% of a proportion, if a distance of 5 exists between those values, one has a much bigger impact than the other. So it's really, really important that we put this over the expected value, because when we divide the observed minus the expected squared divided by the expected, what that allows us to do is think about the relative difference that it has. If something is 1 away from the expected value and we're expecting it to make 95% of the proportion, it's probably going to have a very, very small impact on how different the proportions are. Where if we're expecting something to only have 5% of a proportion and it's magnitudes of order away, it's going to have a very, very large impact on the chi-square. So we want to make sure that we're looking at relatively how far away is the value. We're not looking at how far away is the value in absolute terms, but relative to what it should have made up within the entire mixture. Basically, we're still putting this all over one and we're saying like, okay, what is the difference. All right, so check for understanding. And when we're here, I'll talk about how to figure out what a null and alternative hypothesis is. So Mars Inc. reports that their M&M's peanut candies are produced according to the following color distribution. 23% of each blue and orange, 15% each of green and yellow, and 12% each of red and brown. Joey bought a randomly selected bag of peanut chocolate candies and counted the colors of candies in a sample. What he got were 12 blue, 7 orange, 13 green, 4 yellow, 8 red, and 2 brown. State the appropriate hypothesis for testing the company's claim about the color distribution of M&M's peanut candies. All right, so our proper null hypothesis here is just going to be the company's proportions are true. And our alternative hypothesis is the company's proportions are incorrect. And what that means is at least 2 proportions are wrong. So maybe the company does have 2 of them right. Maybe the company has everything but 2 right. So maybe there are 23% of both blue and orange, but maybe there's actually only 15, maybe there's 15% of red and 12% of green. They have those mixed up or something like that. So 3 of these could be right, but if 2 are wrong, then the company has its proportions wrong in general. And we need to have at least 2 proportions wrong. Because once one proportion is wrong, the other proportion also has to be wrong as well, because they all still add up to 1. So if we go through and we say one proportion is wrong because this clearly isn't it, well, that means another proportion within this also has to be wrong. So that's why I say at least 2. And all this means when we're doing our alternative hypothesis, when I say at least 2 are wrong, that's just saying that these proportions don't add up. Like there's something about what the company has told us and based on my sample I have that does not make sense, and I don't think that the company actually has the correct proportions, and they should go through and retest to figure out what the correct proportions are. Those proportions, again, you could have all 5 wrong, you could just have 2 wrong, but still that means the company's claim about their proportions is incorrect. We might not know exactly what proportions are incorrect right away, but we have a general sense for whether or not they are. All right, calculate the expected count for each color. So, he bought a random bag of peanut chocolate candy. So first we have to figure out what the total size of the bag is. He's got 12 blue plus 7 orange plus 13 green, 4 yellow, 8 red, and 2 brown. So that is... he has 46 candies. So this is his sample size, is 46. So n is equal to 46. Then to figure out the expected count, so for blue and orange, the expected count is 46 times 0.23 because that's their proportion, and there's 46 of the sample size. So when we go through and we look at how many blue and green there are, we should expect 10.58 for both blue and green, or blue and orange, sorry. When we look at green, we are going to be doing 0.15 times, or green and yellow, we're going to be doing 0.15 times 46. And this is equal to 6.9. And then red and brown is going to be equal to 0.12 times 46 for its proportion times the sample size. And each of these should be equal to 5.52. Now you might be saying, Mr. Yehlen, when you add all these up, this clearly does not add up to 46. Well, when you add all these up and multiply, when you multiply each one by 2 and then add them all up, it will add to 46 because we have to multiply the orange and blue by 2 because that's just representing 10.58, we're expecting 10.58 blue, we're expecting 10.58 orange. We're expecting 6.9 green, we're expecting 6.9 yellow, we're expecting 5.52 red, we're expecting 5.52 brown. Since each of them make up the same proportion size, we have the same expected value for each. So now that's the expected value for each color. Now when we want to go through and actually calculate the chi-square statistic, now I'm going to look at what the actual results were compared to the expected. So we had 12 actual blue, and we expected 10.58 blue. This will be squared all over 10.58. We add this to the expected value, or the actual value of orange, which is 7, minus the expected value of orange, squared all over 10.58. We'll do this with green. We had 13 green, with an expected value of 6.9, all over 6.9, plus the yellow, where we had 4, minus 6.9 for the expected value of yellow squared over 6.9. And we will do this with red and brown, plus 8, minus the 5.52 for red, all over 5.52. And then plus 2 brown, now the nice thing is, yes, we're going to get negative numbers as we do this, but since they're all squared, that means that they all end up being positive. We're going to be, and this allows us to look at the absolute distance, or the absolute value of how far away this is by squaring the value, and then we're able to look at the relative absolute value of how far away our errors are here from the expected value to our actual value based on the fact that we're squaring it to compare. When we go through here, you plug this in on your calculator, and you plug this in, and you find that your chi-square statistic is 11.3724. Now this is what the chi-square is. So we say chi squared, which looks like x squared, is equal to 11.3724. Now what does this mean? What is this number in relation? Well, this number is kind of like a z value or a t value. It tells us it tells us a probability of this occurring, or what is this like. Well, this isn't exactly like a t or a p value. A chi-square value is not normally distributed. We can't go through. This tells us something, and it tells us the likelihood of this event occurring. What is the likelihood of all of these proportions being this far away from the actual proportion? This kind of tells us the overall error that we had from our sample size compared to our expected value. And if this is our overall error of our sample size compared to our expected value, what does that mean? How likely was this to occur? Does this tell us that the company is likely lying about this, so on and so forth? So what we have to do is we have to think about a chi-square distribution. Now the chi-square distributions are a family of density curves that take only non-negative values. When we think about this, all of these are positive, and they're skewed to the right. A particular chi-square distribution is specified by giving its degree of freedom. The chi-square test for goodness of fit uses the chi-square distribution with degrees of freedom, the number of categories minus 1. So this is what the chi-square distribution is. If you'll note, we've got 3 chi-squares here, and we're going to see that as the degrees of freedom go, the less and less skewed right it is. So the lower the degree of freedom, the more skewed right your distribution is. The higher the degree of freedom, the less skewed right your distribution is. The more degrees of freedom you have, the more and more it kind of starts looking, I don't want to say normal, but the more symmetric you have, the more even of a distribution you have. If you have a lot of categories, there's a lot more room for error, and since there's a lot more room for error, there's a larger chance to get some values that are fairly far off. Now, there are some interesting things about the chi-square distribution. So the mean, or the average value of a distribution, is equal to the degrees of freedom. The for degrees of freedom greater than 2, so as long as you have, if there are more than 2 degrees of freedom, so more than 2 degrees of freedom, then you end up with a peak at the degrees of freedom minus 2. So if we look here, we've got 3 degrees of freedom, that's more. The peak of this blue curve for the 3 degrees of freedom occurs at 1. With degrees of freedom at 5, we've got our peak for that at 3. And when we look at our degrees of freedom of 10, the peak of our degrees of freedom is at 8. So that happens with all of our chi-square distributions when we are looking at degrees of freedom greater than 2. So degrees of freedom greater than 2, you subtract the number of degrees of freedom from 2, and that's where the peak of that chi-square curve is going to end up happening. And those are kind of the two special cases here. So again, the mean of this is going to end up being 3. It's just equal to your degrees of freedom. The mean of this is equal to 5 because it's just equal to your degrees of freedom. So those are some special cases about that chi-square distribution. Now, what does this mean? Well, when we look at that chi-square distribution, you can see that this is going to end up working a lot like a normal probability plot. We're going to end up saying, like, all right, we've got some chi-square value. Let's say that we had a chi-square value of 14 when we have 10 degrees of freedom. This means that this is the probability of that event occurring. Here's all of those events that didn't occur. Here's where it could happen. The area highlighted to the right is where that event is likely to happen or more, because there are possibilities of getting a chi-square value greater than 14 when you have degrees of 10. It's fairly common because we have a fairly large area there. So we're still going to end up looking for what is the area under this curve, and the area under that curve ends up being equal to a probability value, just like when we look at normal probability plots. So we've got a table. This is table C in your book, but this is your percentage points for chi-square distribution. And again, it's going to work kind of like a T-chart. So for example, let's look up here, and I'm pretty sure this is going to end up being our check for understanding. So we're going to go ahead and continue that analysis here. First, we should look at the conditions for carrying out a chi-square test. So confirm that the expected counts are large enough to use a chi-square distribution. And which distribution specify the degrees of freedom should we use? All right, so first of all, the conditions for a chi-square test, it's random. Joey bought a random bag of peanut M&Ms. That's going to be a random distribution. We're good. 10% when sampling without replacement. Check that n is less than 1/10 n. 1 bag of peanut M&Ms is less than a tenth of all the peanut M&Ms in the world. He probably could have done that just for his store alone, let alone all the peanut M&Ms in the world. So the sample size meets the 10% condition. And then finally, large counts. Large counts for a chi-square is different than our other large counts. What it means is all expected counts are at least 5. So when I go back up and I look at my expected counts here, 5.52, 5.52, 6.9, 6.9, 10.58, 10.58. Perfect. I'm cool. I've got an expected count of at least 5 for each of these, so this works out for me. All 3 conditions work out. The expected counts are all large enough. All of them are greater than 5. 5.52 was my smallest, so we're good. And that's expected counts, not actual. It doesn't matter that my brown one up here, I only had 2 brown M&Ms, I only had 4 yellow M&Ms. Both of those are less than 5, but that doesn't matter because it's not my expected count. I'm concerned with my expected count for my large count values. Does not matter what happens in the actual count. So I can go ahead and figure out what the likelihood of this happening is based off the conditions for my chi-square test. All right, I'm going to use table C to find the value of P, and I'm going to use my calculator to figure out the value of P. So here what I'm going to do is my chi-square value was 11.3724. And I have got 5 degrees of freedom. I had 6 categories. My categories were blue, orange, green, yellow, red, brown. I had 6 categories, so that means I've got 5 degrees of freedom. So what I do here is I go to 5 degrees of freedom on my chart, and I look for 11.3724. So I'm going to go here, and I'm going to look at this, and I'm going to say that, all right, 11.3724 falls somewhere between these two values, and then it's like a t-table. So now I know that my probability value is greater than 0.01, and it's less than 0.05. If I wanted to do this on, so that was for table, that was for number 3. When I sketch a graph for this, I'm going to end up having 1, 2, 3, 4, 5, 6, 7. So since this is 5 degrees of freedom, its peak is going to occur at 3, and then it's going to come down and kind of start tailing out. So then this is what it would look like. This is where the area of my graph would be right here. We found out that my p-value is between 0.01 and 0.05. To figure this out using my calculator, what I'm going to do is I'm going to hit second and then vars to go to my distribution page. So second vars. And then I'm going to go down to option 8, which is x squared CDF. My lower limit is going to be my chi-square score. So in this case, it's going to end up being 11.3724. And then I'm going to make my upper limit a huge number. I think I've done I honestly think I did 1 trillion. And then for degrees of freedom, I've got 5 degrees of freedom here. I'm going to hit paste. Once I fix a couple things here, I'm going to paste it into my calculator once I have that. And I'm going to find that my p-value 0.0447. And I'm happy with that because that is between 0.01 and 0.05, which is what I expected based off of my table C. Now, what conclusion would I draw about the company's claim for color distribution of peanut M&Ms? Well, here, let's assume that our alpha value was 0.05. That's our default alpha. And we're good at this point. 0.0447 is less than 0.05. We reject the null. And we have evidence to suggest that this distribution is incorrect. Based off the way these candies were handed out, one of these distributions is wrong. Looking at it, we could figure out, we could go through and we could break down which one had the biggest impact based off its relative distance. So, for example, the orange M&Ms have a really big difference, but I'd say that the green M&Ms probably have the largest difference at 13 when we only expected 6.9 of them. So they had a really, really big difference. The green M&M distribution is probably wrong. There's probably more green M&Ms. I can just look at that by seeing that that had the largest portion of the chi-square. And then so that means that there's another proportion, at least one other proportion that's wrong to make up for the fact that there's probably more green M&Ms. And that's just based off of what I'm looking at in that formula. But we have enough evidence here to reject the null. We have the conditions for carrying out the tests. And then over here, we just have like a chi-square test for the goodness of fit. And this is just a summary of that goodness of fit. If all the conditions are met to determine whether a category or variable has been specified in a distribution of a population of interest, expresses the proportion of individuals falling into each possible category, we perform a test. Your null hypothesis is always going to be that the stated distribution is correct. Your alternative hypothesis is that the stated distribution is incorrect. We run our chi-square test, and once we have our chi-square test, that gives us a chi-square value. We look at the chi-square value in table C to get a p-value, and then the p-value is the area to the right of that chi-squared, which gives us, based on the degrees of freedom, it gives us the probability of that event occurring. And then again, we're going to use the same alpha standard versus p-value to see whether or not we have something significant and whether or not we're going to be able to reject the null or fail to reject the null based off those chi-square values compared to its p. So here, biologists wish to mate pairs of fruit flies having genetic makeup of big R, big C, small c, indicating that each has one dominant gene R and one recessive gene R for eye color, along with one dominant gene C, one recessive GC for each wing type, yada, yada, yada. This is a Punnett square. So it's giving us the Punnett square breakdown. Any offspring receiving a big R gene will have red eyes, and any offspring receiving a C gene will have straight wings. So based on the Punnett square, the biologists predict a ratio of 9 red-eyed, straight-winged, 3 red-eyed curly-winged, 3 white-eyed straight-winged, and 1 white-eyed curly-wing offspring. So we are expecting 9/16 red-eyed straight-winged. We are expecting 3/16 red-eyed curly-winged. We are expecting 3/16 white-eyed straight-winged, and we are expecting 1/16 white-eyed curly-winged. So to test the hypothesis about the distribution of the offspring, the biologists made random samples of fruit flies. Of the 200 offspring, 99 had red eyes and straight wings, 42 had red eyes and curly wings, 49 had white eyes and straight wings, and 10 had white eyes and curly wings. Do these data differ significantly from what the biologists have predicted? And we want to carry out the test at a 0.01 alpha significance level. So this one's given to us. We don't need to think about it too much. All right, so first we need the expected value. So expected value of the red-eyed straight wings is going to be 9/16 times 200. And when we do that, 9/16 times 200 is 9/16/200 is 112.5. For our red-eyed curly wings, this is going to be 3/16 times 200, which is equal to 37.5. And this is going to be the same thing for our white-eyed straight-winged. We're going to expect 3/16 of those, so this is 200, which is also going to be 37.5. And then for our white-eyed curly-winged, we're going to expect 1/16 times 200. So that's going to end up giving us 12.5. We expect 12.5 there. When we add this up, this is equal to 200, so we've done our math here correctly. We've met the large counts condition in the fact that all of these are above 5, so we're going to be able to carry out a chi-square test for significance. Every one of these, 12.5 is our lowest expected value, and that is greater than 5. So we can go ahead now and we can start measuring our chi-square value. So we had 99 minus that 112.5 squared over 99 for the red-eyed straight wings, plus 42 minus 37.5 squared over 37.5 for the red-eyed curly wings, plus 49 minus 37.5 squared over 37.5 plus 10 minus 12.5 squared over 12.5 for the white-eyed curly wings. Once we go through here and we perform this, once you add up all these values, you're going to end up with a chi-square value of 6.1867. And we've got 3 degrees of freedom here because we've got 4 categories. So if we wanted to plug this in on our calculator, I will hit second vars to go to my distribution page. I go down to number 8. I hit x squared CDF. My lower limit is going to be 6.1867. 0.1867. My upper limit, I keep that at 1 trillion. I'm not changing that. I just keep that as a very, very large number, and I've got 3 degrees of freedom, and I'm going to paste this in on my calculator. And I'm going to find that when I do this, I end up with a p-value of 0.103. 0.103 is greater than 0.01. I guess I should have stated my hypothesis and my alternative hypothesis. So my hypothesis, or my null hypothesis, is that the distribution according to the Punnett square is correct. And then my alternative hypothesis is the distribution according to Punnett square is incorrect. So now I know that because my significance level was 0.01 and my p-value of 0.103 is greater than 0.01, I fail to reject the null hypothesis. I don't have enough evidence here to suggest any differently. So this does not necessarily mean that the distribution is perfectly related to the Punnett square, and the Punnett square has the correct distribution. I just don't have enough evidence in this case to negate that claim. This claim is the way it is. So I don't have enough evidence here. I fail to reject the null hypothesis. I don't have the evidence. I don't have enough to suggest that this actually isn't going to rely off what the Punnett square dictates. Now, again, I could also have gone up here. I could have looked at my C table. I could have looked at 3 degrees of freedom, and I could have found where 6.1867 occurs. 6.1867 occurs somewhere between these two values. So that means that my values would have fallen somewhere between 0.25 and 0.1. And when we look at my p-value as given by the calculator to be at 0.103, that does fall between 0.25 and 0.1. So that gives me a little bit of extra confirmation here. I feel very, very confident in my answer. So that's how we go about performing an entire chi-square test. It's a little bit annoying in the fact that you do need to find your expected values. You have to go through, you've got to get your expected values because the whole chi-square test is related to the expected values. Even when you do this on your calculator, you got to do it via the expected values. I'll show you in class how to do it on your calculator. You guys have a homework assignment tonight. If you have any questions or concerns, please reach out as soon as possible. Have a great night.